What I tried to show you last time was the usefulness of the phase space. For instance, we saw that when we look at the momentum space and we consider the motion of planets, it clarifies things enormously because it explains why the orbits are closed. We saw that it's simply big circle. The orbits are simply big circle, but not that would be impossible to discover if we limit ourselves with the x space, so to say, with the coordinate space, with the configuration space. That's synonyms. But in the momentum space, it became immediately clear. Then we also looked at some very general feature of the Hamiltonian motion, which applies to all Hamiltonian systems. And that was the Poincaré recurrence theorem. Let me also remind you a couple of more technical things which we discussed and which we will need today. First of all, this is something to be remembered, actually. First of all, we said that Hamiltonian system is given if we are given the phase space. And so we have some coordinates, we call them y alpha, and we postulate or assume given what is called the Poisson brackets of these coordinates. This is obviously anti-symmetric tensor, but it's not an arbitrary anti-symmetric tensor. We said there is a Jacobi identity to be satisfied, but otherwise, if you say that the Jacobi identity is satisfied, then this is a legitimate Hamiltonian system. There are also some conditions of secondary importance that it should be invertible. And also the inverse of this, we said, is called the symplectic structure, and sometimes it's actually important to keep in mind both of them, because sometimes one is more convenient, sometimes another. So last but not least, to have a Hamiltonian which is an arbitrary function on this space. And the most typical example, which the vast number of examples, the phase space can be is of a simple type. It's just you have p and x equal to 1, or more precise, if you have many degrees of freedom, you have Kronecker delta, and all other brackets x, you split y's, so y is p and x. I'm just repeating what I have said a couple of lectures ago. And one more very important notion for today, which we also mentioned, is the canonical transformations. Canonical transformations are transformations which don't change the Poisson brackets. So you consider in this particular case, we look at some arbitrary transformation of or of the phase space, and you plug it in and demand that Px is 1. So the brackets don't change. And from that, we get a relation for these things. By the way, one more rule which I want to remind you about is that more or less by definition, if you have two functions on the phase space, you define the Poisson brackets in the following way. You simply say roughly speaking, you are saying this is a commutator in some sense. This is also a commutator, and it's non-zero because y's don't commute. So that's, but the rule is very simple and natural. You simply say we vary a little bit this y, we vary a little bit this y, and we multiply it by the brackets y alpha, y beta. That's the general rule which allows you to calculate the brackets. Why I'm interested in this? It will become clear a little later. At the moment, I'm just reminding you of what we already discussed. Now, one more thing, one more reminder is that we can also define when we have the action in this case, or the action was in general case, and now I want to ask you, from the point of view of the action, I just want to describe canonical transformations in terms of the action. So let's take a simplest case like that, although it doesn't really change very much. But let's take it. So what do you think the condition for the transformation to be canonical? So we now, when you look at this action, what you consider this general transformation. For simplicity, I'm just considering two-dimensional phase space, but this is true in any dimensions. You have some transformation which depend on, here it depends on two functions, but we impose this condition and get only one arbitrary function. How to formulate the condition that transformation of coordinates is canonical in the action? I shall, to make the my point, I shall also add that the advantage of when the Poisson brackets are unchanged, this was a definition, so is the form of the Hamilton equation. So here we have, if we have the Hamilton equation P dot dh dx, x dot dh dp, which we derive from here, and if we perform canonical transformations, what will be, how this equation will look in terms of p tilde and x tilde? What is, I now want to change variables, or I can write down tildes here, and I want to go to the original variable. That doesn't matter. So what will be the form of the Hamilton equation in I want to remind you that general Hamiltonian equation is that you have the commutator or Poisson brackets. That somehow is interchangeable terms. So when I have this form, what can I say? How the equation will look in terms of tilde variables? What will change and what will not change? Sorry?
Does the Hamiltonian stay the same and y alpha in the bracket change?
Just a little louder.
Does the Hamiltonian have to stay the same?
The Hamiltonian is not, well, let me give you the answer to this. Actually, the canonicity means that so the Hamiltonian H tilde, it's H of P tilde X tilde X of X tilde P tilde X tilde. So the Hamiltonian changes when you change variables. We will see in a moment how it changes. The Hamiltonian changes, but the structure of equation remains the same. The structure of equation, the form of equation is unchanged. And now, I don't really want to spend too much time on that, but on the other hand, it must be understood. It's some real basis of Hamiltonian dynamics, and this Hamiltonian dynamics permeates all physics. So that's my excuse for spending some time for formalities, which I don't like. I much more prefer some beautiful physical applications. Formalisms are generally a very dangerous thing. People get involved in it and then forget about why they need it in the first place. All right. So what should we demand from this change of variables, and what basically the condition that this variation coming from variation principle coming from this action will generate the same form of equations? How the action should look in the tilde variables? That's the question. Try something natural. Try to remember how by variation we derived it, where this minus come from, and so on. Well, remember that the whole structure was the symplectic structure, which is the inverse of this, and it is precisely because of this term we get this thing. So the condition is that when you change variables, the Hamiltonian may change. You see, if you simply change variables in an arbitrary way, then both terms will change. They will be unrecognizable. Now, we don't care about the Hamiltonian. Actually, we care, it will be good that it is changing under canonical transformations. But the first term must be the same as before. Only then you will get this equation. it all comes, this structure comes from the first term here. And so that actually gives you the condition that when you go to the new variables, it should be the same as old variables plus maybe a total derivative. That's the condition of, under this condition you have the same, you will have symplectic structure unchanged and the Poisson structure unchanged. You still may be in the dark why we need this, but the point is that by changing these variables, sometimes you can simplify the Hamiltonian drastically, and that's what we're going to discuss now. Simplify, and then it gives you a qualitative picture of motion of the system. But here it's kind of a, in a nutshell, I try to describe the most basic points. And by canonical well, we now will introduce one more idea, and then we will go to applications of this formalism. One more thing is the following. You can sometimes, by canonical transformations, you can, well, one more reminder, which we will need, the general infinitesimal form of canonical transformation so you have a variation of p and x, and the general form is you have an arbitrary function of p and x, and if there are many coordinates, then there is just an index I here and here. So it's precisely, it looks precisely like development. This infinitesimal transformation is precisely like f plays the role of some other Hamiltonian. And let me give you an example, which we will need actually. The example is, let's f can be arbitrary function here on the phase space, and you see that the number that canonical transformations they're defined by one generating, it's called generating function, and this function defines the transformation. Mathematically speaking, by the way, there's a whole branch of mathematics which was created out of this. It's a geometry, the so-called symplectic geometry. It's a geometry invariant under canonical transformations. And there are plenty of beautiful results there, but they're mostly purely geometrical, very strange geometry. They're not really, don't really have much application to physics so far. All right, so I was going to give you an example. Let's suppose that we have four-dimensional phase space. And we will be looking at some Hamiltonian. And I want to look at the canonical transformation generated by the function L, which is p1x2 minus p2x1. I will just choose this, and now let's see what kind of transformation it generates. All this is a special example. Let's just try to see. So what is delta P1, for instance? Can you dictate me delta P1? How changes the... Yes, it is equal to delta P1 is minus dl dx1, and so it is P2. Delta P2 will be minus x1. Delta x1 will be dl over dp1, so it will be x2, and delta x2 will be minus x1. That's elementary algebra. Now, what it all means, what kind of transformation we performed actually. What infinitesimal transformations have this form? It has precise geometrical meaning, this this transformation. Geometrical and physical meaning. So suppose you have concentrate on X. What kind of transformation is this? So you have two-dimensional space, easy to imagine.
Rotation.
It is rotation. Remember, the formula for rotation is x1 cosine for the finite rotation in two dimension. X2 will be now we take infinitesimal limit. As theta goes to 0, you get theta x2, you get minus theta x1. And when you know infinitesimal transformations, infinitesimal rotation, you actually you can integrate, you can obtain the finite one by successive application of infinitesimals. More precisely, you can integrate infinitesimal rotation to get a finite rotation. So we see that we have rotation in the phase space. So
sorry, should that be a P1 in the second equation?
This one?
Yeah.
Oh yes, that's P1. Thank you. It's all comes from this formula. And now we can ask the question, what will be the Poisson brackets of, so the function L generates rotation in the phase space. And now let's think of what is HL. What do you think it will be? So we'll let's write it down. Write down general form. Sum over k. We have dH dpk, dl dxk, minus dH dxk, dl dpk. Or you can write that using this formula is just sum delta pk dH dpk plus delta xk dh dxk, where deltas are. So what is the result of it? If you, what do you think it should be?
0.
Actually, yes, if u is x1 square plus x2 square, then the result should be 0, because it is just the rotation, and we are checking that this thing is rotationally. It's obvious that it's rotationally invariant, so this transformation will give 0. As a result, we have HL 0. On the other hand, we know that for any function L dot, whatever function L is, we have this equation. So what is the physical meaning? Now the physical meaning of this example. What is the meaning of the function f? Oh, function L, excuse me. Look, we calculated that canonical transformation here gives us 0. So this function is some conserved quantity, and now you have to figure out what kind of conserved quantity is this.
Is it conserved under the transformation?
Which transformation?
The infinitesimal transformation.
Well, again, these are infinitesimal transformations, okay? We learned that these transformations are generated by function L. So these are canonical transformations which don't change the Poisson brackets. That's number one. Second, we realized that this is rotation in the phase space. This is just rotation. Third, we realized that under such rotation, the Hamiltonian is invariant, and so Poisson brackets of the Hamiltonian with this function must be 0. So let me say it again. I really want you to understand this. The function L is a function on the phase space. Generally speaking, then the system moves, P and X depend on time, and L will depend on time. However, we know that this time dependence is the brackets of H and L. Now, L, and in this context, this L is just some physical quantity which I want you to identify, but that's another matter. But it also plays another purely geometrical role. It generates a symmetry in the phase space. So it is actually, it generates symmetry, and it was symmetry under rotation. And the Hamiltonian was invariant under this symmetry. But invariance of the Hamiltonian, what the general rule is, if H invariant under canonical transformation, this is a purely geometrical fact, that this function H is unchanged under particular canonical transformations generated by, say, function f, or whatever you call it. So when I say generated by, I mean this formula. Okay? So the function is given, and you differentiate, you find it. Then what is the consequence of it? Suppose you have a Hamiltonian invariant under canonical transformation. Again, generic canonical transformation. Under generic canonical transformation, the Hamiltonian is not invariant. It doesn't have to be. But suppose that, as is in this case, that there is such thing. Then what is the consequence? Just think about it. I'm just rephrasing what we discussed a minute ago. What is this condition in terms of the Poisson brackets of H and F? The invariance of the Hamiltonian. It's the condition is that the Poisson brackets are 0. Instead of writing these words, I could just write down this thing. That's the condition for invariance. And this condition for invariance, what is the physical aspect of it?
That F is conserved.
Yeah, that F is conserved. So we're talking about Noether theorem, but generalized Noether theorem. Noether theorem in the phase space, not in coordinate space. So you see, there is a very interesting interplay between geometry and physics here, and namely the function which was purely geometric meaning, it just defines the infinitesimal transformations, turns out to be conserved integral in the system. Conserved integral means that its time derivative is 0. Well, now returning back to our example, you should identify what is the physical meaning of this thing. What is this function L?
The angular momentum.
It is the angular momentum, yes. So we see that the function which turns out to be, or it's actually, we call it angular momentum. We don't have to. Just some function L which generates some canonical transformation, which the Hamiltonian is invariant, so therefore Hamiltonian commutes with this L, and that leads to time preservation of L, leads to this equation. And so we get the constant of motion directly from geometry of the phase space. Now let's one more think about this matter. I was wrong. I will need this. What if, as we saw, it generates x2 and so on. What if I try to treat L as a Hamiltonian itself? Suppose I want to write down the Hamilton equation with respect to some, I will call it a different time. Let's call it S instead of. So let's suppose I shall write down the equation which is just the Hamilton equation, but I just pretend that this is a Hamiltonian. So to be concrete, let's write it down. Dx2 ds. And now I'm asking you, what's the what is the solution of this equation and what it means? So I took angular momentum instead of the Hamiltonian, and Hamiltonian generates time development. I have another function on the any function on the phase space actually generates some development with respect to some parameter. I call it S in this case. My question is what it means. Suppose I solve this equation. What is the what will be the answer? And actually, although you may not realize this, the answer is written somewhere on the blackboard. The solution of this Hamiltonian system is somewhere. Yeah, go ahead.
You should just rotate it.
Yes. So the solution of this will be simply this formula where theta is replaced by S. So you see that the Hamiltonian in this angular momentum indeed generates rotation. Now one more useful thing. I'm still.
I'm sorry.
Yes.
So that statement that is written, so that should only hold true for infinitesimal.
Say it again.
Shouldn't that only hold true for infinitesimal canonical transformations?
Yes. This is infinitesimal canonical transformation. Okay, but I'm now integrating. Here I wrote down. I'm saying I have delta x1, which is x2, delta x2, which is minus x1, and this is infinitesimal. Okay? You may ask now the question, how, by knowing, I should be able to reconstruct finite transformations if I know infinitesimals. I should, how I do this? I would say that I would consider the function of theta, and x2 will be the function of theta, where theta is the angle of rotation. And now suppose I have some theta, and then I rotate, I go from theta to theta plus delta theta. I shall rotate it a little bit. Then I will find out that that my variable, it's purely, actually, this part, it doesn't have anything to do with Hamiltonian. It's pure geometry. Pure geometry, let me say it again. When you have a group of transformations and you know infinitesimal transformations of the group, you can integrate it to the finite transformation. How you do this? You introduce a parameter, and then this simply translates that the change of x1 from theta to theta plus d theta is x2, and dx2 d theta x1, and then you solve these differential equations and you get this formula. That's how you integrate. It's less trivial when you have non-abelian, non-commuting rotations to which we are coming, say, in 3 dimensions. But in 2 dimensions, although there also you can, there's, when you have a continuous group, group, the word group means that the two consecutive transformation belongs to the class of transformations, that you can take a product and it will be a product of transformation, it's transformation again. Then there is a standard prescription for obtaining finite transformation from infinitesimal transformations. And the simplest imaginable example is this one. Okay, now we can also use this canonical transformation. That was basically my point at the beginning, that we can use it in such a way as to simplify the Hamiltonian. In particular, I'm still need one more small thing, sorry. One more small thing is that suppose you have two consts, not one L, but two, but you have some other integral motion. For example, let's take this Hamiltonian. Notice, by the way, that how those things come. They are just can be interpreted as different as multi-time picture. You have time, canonical time defined by the Hamiltonian, but you also have other, so to say, times defined by other generators. And in this case, we have clearly at least two. We can write down L1, which is P2x3 minus P3x2, and we can write down L2. 1, 2, 3, 2, 3, 1, P3 x1 minus p1 x3. So we have two, this is rotation in the 2-3 plane, this is rotation in the 3-1 plane, okay? Now, when you have any two conserved integrals, you can conclude, and these are components of angular momentum, you can conclude that the Poisson brackets of the two, we can calculate it, and this Poisson bracket will be a conserved integral again. Why is that? Why do you think, how we approach to this? So I claim that there is the following statement, that if L1 and L2 commute with H, commute means Poisson brackets are 0. So let's suppose that HL1 and HL2 are 0. From this, so L1 and L2 are integrals, conserved quantities. Now, what about the commutator, the Poisson brackets? I claim that it is also an integral. How to prove it? It's all simple. Yeah, go ahead.
Can we use the equation you wrote earlier with the bracket of y alpha and another bracket plus cycles equals 0?
Yes, this is what is called the Jacobi identity. And it says that ABC plus cyclic permutations is 0. And so you will have, if you calculate H L1, L2, plus you get L1, L2H, plus you get L2, HL1 is 0. I hope you notice that I'm writing it in this form. So from here you immediately see that if this is 0, then this is also be 0. So the Poisson brackets allow you to get new integrals from the old ones. When you have 2, you always can take a commutator. And by the way, when I was writing this, I hope you noticed that the rule. Of course, I don't remember the order of these factors, but a mnemonic trick is very simple, which allows me, without remembering, write it down. You write the first term, and then the first letter becomes the last letter, and then the first letter becomes the last letter again, and so on. So there's a very simple mnemonic rule for writing down these cyclic permutations. And it's useful. And now the one more, for I didn't intend to have so many formal things today, but this is, suppose we calculate now the L1 and L2. What will be, guess what will be the geometrical meaning of it? It will be, we know that it will become the integral. L1 is rotation in 2, 3, or around axis 1. L2 is rotation around axis 2. Suppose we take the Poisson brackets. Yes?
It could mean how L2 changes under a rotation under L1.
Yes, but not quite. It's just how it commutes. So you perform infinitesimal rotation. You perform infinitesimal rotation L2, then L1, and then in the opposite order. So it is a commutator. And when you look at the rotation, when you calculate this, you will find, guess the answer. It will be L3, yes. Rotation around axis 3. You can check it yourself by different. Well, that's the algebra is elementary. You just need to know what you have to do, but calculations are very easy here. And indeed, it shows you the geometrical meaning of all these things, because this relation can be interpreted in 2 ways. One, it was the generation of the new integral of motion, but the other is purely geometrical. It's just commuting rotations, nothing more than that. And as I showed you for finite rotation, it's obvious with some object like this, that 90 degrees rotation here, 90 degrees here is not the same as the opposite order. And that's what the formulas tell us. They tell us for infinitesimal rotation, but okay. But now finally, it was a somewhat extended trip into Hamiltonian formalism. What I really need is to introduce the notion, very important notion of completely integrable systems. Namely, sometimes it is and their motion, and that will bring us to statistical mechanics. You see, my the thing is that Hamiltonian dynamics were wrapping up with it more or less because we need to discuss hydrodynamics, statistical dynamics, chaos, and so on. But it, as you can see by itself, you can spend a whole year discussing various subtleties of Hamiltonian dynamics. It's very subtle and well-developed subject on which great mathematicians work and contributed a lot, not to say nothing about physicists. But there was a wonderful contribution by such mathematicians like Poincaré and Kolmogorov and so on. So we have to to approach to the end of this discussion. But still, it's very important to know that we can introduce variables which are in which Hamiltonian, which are called action angle variables. The philosophy is, let's try to simplify, to use canonical invariance under change of variables, to simplify the system as much as we can. It's basically, all this appeared not by someone trying to invent new formalism, but people were solving concrete problem of celestial mechanics. And they found hundreds of tricks to simplify this. Surprisingly, celestial mechanics even today is not a finished subject. Actually, it's quite curious. Let me digress to give you a rest from the formalism. Quite curious that the problem of three bodies is not completely solved. It's a very complicated problem. It's much more complicated than the problem of three bodies in quantum mechanics. When you have an ion of helium, it is actually, or ion of hydrogen, it's when you have three-body problem, it's much easier to solve. So atomic problem, again, that's the same thesis which I mentioned to you, that quantum mechanics is simpler than classical mechanics. Anyway, enough philosophy. Let me introduce the action angle variable. We want to introduce, we have original variables p and x. We want to make canonical transformation to new variables, which I will call I and phi, following the traditional notations. I is a new momentum, and it's called action variables, and phi is angle variables. And the key point is that the original Hamiltonian become a new Hamiltonian, which depends on I only. Let's try to see if it is possible. And if it is possible, then it is really very convenient thing to, then you can draw some interesting conclusions. So action angle variables are just canonical variables with the same Poisson brackets, but such that your Hamiltonian depends only on momenta. It's a canonical momentum, so it depends only on momenta. And we can try to do it first for the Hamiltonian. Let's take a harmonic oscillator. The Hamiltonian is equal, so it's example. harmonic oscillator. And let's try to change variable in such a way that that the Hamiltonian is a function only of momentum. So the Hamiltonian, let's look at the, let's try, what is natural here is first to try the spherical coordinates, or not spherical, just to write down P as R cosine phi sine phi. Let's change this variable like that. Then the Hamiltonian will be 1/2 of R square. And at the first glance, that's what we need, because then if you interpret R if you try to interpret R as momentum, you will get the Hamiltonian, which depends only on this momentum. But it's not quite right yet. What's wrong? What do you think is wrong with identification of R, if R is what we have to check, better to say, when we have general change of variables, what we have to check to see that it's what we need.
Needs to be canonical.
Yes, exactly. We need to check whether it's canonical. So if we try to do this, how to do this? It's just that if you assume that it's canonical, let's try to do. Let's see if they're canonical or not. Then you have dp dr dx d phi minus dp d phi dx dr. Let's calculate it. dp dr is cosine phi. Now dx d phi is r cosine phi. And here you will have, from here you will have sine square phi. So you will find that it is r. It's not 1. So this simply passing to polar coordinates is not a canonical transformation. You see? But it's pretty close to it. Namely, very easy to check. By the way, one of the other ways of seeing it's not quite canonical, not exactly canonical transformation, is to write down the formula r dr d phi. And dp dx is supposed to be unchanged under canonical transformation, and it's changing. So we cannot identify r with momentum. So, but what can we do? It's pretty close, actually. By small changes, you actually will make transformation canonical. I'm asking now, what is it? What is
Replace phi with phi over r.
by what?
Phi over r.
Well, then it will be a mess with differentiations here. Actually, so we are looking at variables I and phi, and we want dp dx to be di d phi. That's that's true for canonical transformation. And you see that I, if you choose I, is simply 1/2 r square. Then everything works. And you actually have the Hamiltonian, which is precisely equal to I. Now, when we have actually in the general one-dimensional system, it's quite easy to write down this thing. I shall tell you what it is, but just in one moment before that. So when H, generally speaking, for any one-dimensional system, H will be a function of I. It's not will be linear in I, but and then we will have the following Hamilton equation. And the angle variable, the motion in the px space, the constant Hamiltonian corresponds to a circle, and the angle corresponds to the angle in this diagram. So all we have done is just we replaced r by square root of 2i. Now, as I said, generally the angular velocity depends on this action variable. For harmonic oscillator, what was the meaning of the fact which we found by calculation that the Hamiltonian is linear in I? It is a special property of harmonic oscillator. What do you think it corresponds to? There is a simple physical feature of harmonic oscillator which is reflected in this. Well, look at this equation and think what it means. If H is linear. What is the property, the basic physical property? Yeah, go ahead.
Its speed and phase space is similar.
The what?
Its speed and phase space is constant.
The what?
Speed.
Speed. Yeah, well, it basically means a very simple thing. It simply says that angular velocity, velocity of rotation in the case of harmonic oscillator, does not depend on the amplitude. For a small mathematical pendulum, the frequency is amplitude independent. The amplitude is actually defined by energy and by I, but generally it's just that. Well, there is you can easily find now from the relation dp dx should be equal to di d phi. You can easily find the general one-dimensional action angle variable. Namely, you can simply integrate from here. You find that 2 pi I is integral over the trajectory p dx. So basically the meaning, and that defines this action variable. In this case, E or H will be some, you have to invert this integral and find H of I. And it has a very interesting meaning, actually. Let's try to get some understanding of the meaning of these angle variables. And once again, it turns out to be some elementary quantum mechanics help enormously to understand this, although it's introduced purely classically, but it is actually, its meaning becomes clear in quantum mechanics. Okay, let me remind you how Niels Bohr determined the spectrum of hydrogen atom. What I will be saying, it is quantum mechanics, but it's very elementary and it's on the level you definitely know. He just postulated that atom can have a stationary state, En, that there are discrete states in which electron can be, a discrete set of state. And then if you go from the state n to the state n minus 1, you emit light. And the frequency of light in the units when Planck constant is 1 is simply the frequency of, that's the frequency of emitted light. And that's the postulate which turns out to be working in, which is turns out to be exact. But now there was the wonderful derivation which he gave further. From this alone, you don't know what to do. You cannot, don't know how to calculate these things. But then he postulated that when n is much greater than 1, so when the orbit is very large, it should be described by classical mechanics and classical electrodynamics. That was what is called the correspondence principle, that at large quantum number, quantum mechanics, at large scales, quantum mechanics becomes classical. But in classical physics, when you have electron rotated around a nucleus with some frequency omega, it emits photons, and in classical electrodynamics, the energy of these photons is the frequency of light emitted is just the angular rotation, the frequency of this angular rotation. And so he simply replaced for large n, he said it should be equal to the omega, which also depends on En. Or it depends on n. So when we have a classical oscillating system, we actually can calculate the period, and we have this. Where shall I? Yeah, this thing, and this we can calculate classically. So, for instance, for harmonic oscillator, and it gives you the spectrum. For harmonic oscillator, the oscillation frequency is energy independent, and we derive that for harmonic oscillator, it's just it's just constant frequency multiplied by n. So you have plus constant. So you have equidistant energy levels. for more general mechanical system, we have basically what determines the frequency is dx divided by velocity. So you have dx square root of d minus u. And that defines the period of this, the period of the motion. And so you can write down the general expression for, say, hydrogen atom and obtain that En is inversely proportional to n squared. He got the Rydberg formula, the empirical formula, and that was a great success. There is, by the way, there's a side remark to this, is that it's not an exact procedure, but it's kind of interesting. What you get by construction is only a good approximation to exact quantum mechanics, when n is much greater than 1. However, in the case of hydrogen, for certain reasons, this approximate formula is exact. And that was a great luck for the historically, because people reacted, the formula Bohr obtained coincided very precisely with experiment, and it impressed people enormously, and it started the development. Although there was, if it would be any other system, he will find only approximate formula, which is not precisely describing experiments, so it probably will be a different story. But anyway, returning to our case, what would this, let's return to action angle variable. Maybe you can tell me why I'm telling you this story. The formula written on, there are correspondence between the formula, different formulas written on the blackboard, and this one. Namely, I want to ask you, what is the meaning of quantum number n when it is very large? How it relates to what we discussed before? Especially look at this. Look at this formula and try to establish connection with the Bohr's argument for quantized orbits. There are two formulas which are the same, but written in different letters here. By just changing the letter, you will obtain from one formula another. Just concentrate on this one, what it reminds you.
It looks like the phi dot equals partial H.
Exactly, yes, yes. Actually, as n goes, the quantum number of the trajectory goes to infinity, and n becomes the action variable. And you see that frequency, angular frequency of rotation is just the derivative with respect to angle variable, to action variable, and this is precisely this formula. So what I'm saying is that the classical limit, this formula and this formula are the same. And it allows, it explains that the procedure of quantization is simply to say that you first determine the action variable, and then you quantize it. You say it must be integer. And that's what is called semi-classical quantization. It's not precise. It's true. It works. It is precise in harmonic oscillator and in hydrogen atom. It's not precise in general, but it's asymptotically true for large n. So once again, you have orbits characterized by discrete number, by the quantum number n. In the limit of large numbers, these numbers become action variables. Now, why it is, I will still have a minute to tell you why it is useful. I will give you an example. Namely, suppose it's the example which refers to so-called adiabatic invariance. Suppose you change parameters, you change the Hamiltonian in the system very slowly. Then, if generally speaking, arbitrary variable will change, it will change slowly, but if you wait for a long time, it will change considerably. For example, if you look at the energy of the system and you change the Hamiltonian, the energy will change significantly if time is large. But there are quantities for example, if you have harmonic oscillator with time-dependent frequency. It is possible to see that there are certain quantities, energy changes if you change frequency. But the ratio e to omega doesn't change. So there are quantities which are especially stable under adiabatic changes of the situation. Okay, now the derivation in classical mechanics that this is the case is a bit complicated. And it basically says that those action variables are adiabatic invariants. Now, in quantum mechanics, it's completely obvious, because if the system is on the nth level, and if you change things slowly, that means that you introduce the field which cannot supply energy for the system to jump to another level. The slow varying fields, they say photons of very low frequency, they cannot excite the system. And so some rather complicated story, this is just the rather complicated story in classical mechanics becomes completely obvious in the quantum case. Okay, let's stop here, and next time I will clarify a few things about it, and we will move. I actually hoped we will go further than that today, but I think this is important to understand.